Ça marche. Hello, everybody. We're going to start. Thanks for going to this session at Eclipse Conference. We are going to talk about models and patches on models. First of all, who we are. Here is Abel Hegedus from Inquiry Labs. And I am Olivier Constant from Thales. And also there is Mathieu Helbois, who was pretty much the initiator of the work we're going to present, but unfortunately he couldn't be here, so tribute to Mathieu. In a nutshell, what we are going to present is a model patch technology that is intuitively patches for models. It's a new technological component of the Eclipse EMF Diff merge project. So if you're interested after this talk, of course we can discuss. You can ask questions on the forum of the EMF Diff merge project, or you can have a look at the wiki. Since I'm an industry guy, I'm going to explain the why, the needs, so the non-fun part, basically. I'm going to talk about processes and all that stuff. So hopefully in the second part, Abel will come and save the session by presenting fun stuff about what there is actually in the technology and how we can use it. Thales, okay, we work in many different domains and we do complex systems. What is important here is that the systems we work on, they have an increasing complexity, and now it's so high that model-based model-based system engineering, MBSC, is really mandatory. And this is the reason why we worked on a dedicated modeling environment called Capella. So probably most of you have heard of it since well, we spoke quite a bit about it at EclipseCon this year and also at the Capella Day 2 days ago. And also, you may have heard of the industry consortium, the IC, Capella, that has been created within the umbrella of the PolarSys industry working group at the Eclipse Foundation. Let's be a bit more concrete. How do we use Capella? It's not as simple as we might think. We have Capella, okay, so how do we do model-based systems engineering? Well, Capella enforces a certain system design method that is named Arcadia, and Arcadia proposes to divide the design of a system into different levels of abstractions which correspond to different steps in the design process. So I won't give too many details on that. What's important is that, of course, it has to connect with the upstream engineering environments, like, for example, whenever you have requirements in a DOORS database or in requirements in other formats. For example, we have, so Capella is in open source, and we have also a certain number of add-ons for Capella in open source, and there's an add-on that allows you to create requirements in a model form and import them from a data set and link model elements in Capella with those requirements. And of course, symmetrically, there must be a transition bridge from all the system architecture defined in Capella to downstream engineering workbenches. For example, it can be, so you have the system architecture, but then you have certain components. For example, let's say components that are identified as software components, they will be refined with workbenches dedicated to really software engineering. It can be UML, based on UML, it can be based on DSLs, or whatever, and there's typically code generation when possible. But that's not all. I mentioned the different levels of abstraction provided by Arcadia. This can be considered as different viewpoints on the architecture of the system we are designing. And you can see them as core viewpoints. But the idea is that we complete the systems engineering vision with additional viewpoints which correspond to what we call specialty engineering. For example, people working on the performance of the system, people working on the safety, on the costs, on the weight, whatever. The system architecture must integrate all these different visions, or said otherwise, all the different specialty engineerings that plug to the system engineering work must must work in a coherent way, in a consistent way with the system architecture. So they must plug to Capella. So you can extend Capella with viewpoints. The notion of viewpoints is defined in the ISO 42010, by the way. But that's not all, because most of the time, specialty engineering disciplines have their own tools and concepts that are really dedicated to analysis, simulation, or any kind of study and refinement of the for the system architecture defined. So the data or the models defined with these tools must also bridge with the different viewpoints that are plugged onto Capella, right? So if I summarize a bit, this was a hard slide, don't worry, the rest will be a bit more simple. You have the system description according to Arcadia, and you have also the co-engineering work that results into data that is synchronized with the systems engineering, the system architecture defined in Capella. And the whole stuff is the complete system description. But, if I summarize what I've said about transitions and bridges, you can notice that there's a need for model merging and model synchronization everywhere, basically. I say model merging and model synchronization because it's essentially the same thing. Whenever we have a transition bridge, it's an incremental model transformation. Like, for example, you have your system engineering components and you have a set of software engineering components. They must be consistent in terms of interfaces, for example. So whenever you make a change on one side, you want to propagate it to the other side. So you transform to be compliant to the target meta model, and then you diff merge with what you already have in order to see the changes, right? And conversely, a merge is a model transformation also. So it's the same nature. So you have synchronization everywhere. But that's not all, because, well, systems engineering is multi-level. So what I described here, you can have it at the system level, but you can have it at the subsystem or component level. And you have all of these again, and everything must be consistent. So we have synchronization everywhere. Okay, now I've spoken with synchronization on the process level. Now if we speak a bit on about collaboration on models, what we do at TLS is we use classical version control systems like ClearCase, SVN, or Git to manage our models in a classical way. But whenever we need to, we have identified a modeling activity that requires a team of users to work on the same model. In that case, we use Team for Capella. It's an extension of Capella based on CDO and on the collaborative extension of Sirius. And it allows a team of users to work on the same model fluently by using logs at the level of model elements. So on this, we don't need synchronization, right? It's managed automatically. Except that since we have version control, even though it's on coarse-grained branches, we still have the need for merging again. In addition to that, we also have many cases where synchronization, reuse, merging happens in a completely informal way, outside any formal workflow, just because of opportunistic reuse needs. For example, we have two models defined independently, and people want to transfer the data, the model elements from one model to the other model. They're unrelated, completely unrelated, but still. And so we need to be able to do that. Now with the diff merge that's embedded in Capella, EMF Diff merge, you can do that. You will be able to do that in the next version of Capella, and it's already available in the bleeding edge builds. So anyway, if I summarize, model synchronization is everywhere because of the engineering process. We are multi-viewpoint, multi-environment, and multi-level, because of classical version control, and because of opportunistic reuse. And we saw that there is a need for more flexibility. Now we have the technological bricks that allow us to do all I described consistently. It's okay. Technically, it's feasible. Making it easy for the end user to do is another problem, right? And it's a difficult one. But okay, at least from a technical viewpoint, we know how to do. But we noticed that there was a need for more flexibility for the end users, especially there are cases where it's a bit awkward to require that the source and the target models we want to synchronize are available and loaded in memory at the same time. Second point, sometimes it's useful to be able to decouple the time where the diff is computed from the time the merge is done, so the diff is applied in a way. And third point, it can be doing merges can be complicated. You may have to make a certain number of decisions, and sometimes it's useful to, once you have made a certain set of decisions, reuse this set of decisions in other contexts. So if I synthesize this, what we need is patches in a way, hence model patches. So thanks to these fantastically beautiful pictures and very clear ones, you can perfectly understand that this is clearly a patch. Now this is a comparison, it's symmetric, but if you choose a direction, you can extract a patch, that's what we need, that can be applied to a completely different model. So it seems that this is what we need. Clearly, there are some usage scenarios that we have identified, but our impression is that this kind of technology will be useful in many other different scenarios that we have not discovered yet. We have the feeling that a technology that would allow us to do that would be really a technological enabler. And hence, we started to work a bit on that in order to anticipate the needs we're going to have. And because it's a technological enabler, it's really a technology, it's relevant in our point of view to put it in open source. Because, well, what we don't put in open source is the know-how of our domain engineers, like people who build satellites or whatever. We don't want to put this knowledge in open source. But a pure technology, it's okay for us, and it's better because we can collaborate with others. Model patches is nothing new. Actually, in a way, it's just what we do with code applied to models, in a way. You can think of the relation with the EMF notifications that allow you to know whenever there's a change in the model. There's also the EMF change model that allows you to do undo redo, right? If you take technologies like CDO, you have deltas already. But all of these are for things that, these technologies, these notions are not for portable deltas, self-contained deltas. So it's not patches. You can think of comparison framework like EMF Compare, obviously, EMF Diff merge, which is more at a technological level for synchronization and merge. But these are really for comparison, and again, they produce symmetrical results and not deltas that are self-contained and portable. There have been attempts in the past, MPatch and EPatch within EMF Compare, but these were abandoned attempts. They are not maintained anymore. I think it was more in an academic perspective for reflecting about the concepts, but it's not maintained. So anyway, on our side, we have the impression that there are clear industrial needs, and we decided to work on it. And since you seem to be still alive, it's okay, because Abel is going to present the fun.
Okay, so hello, I'm Abel from Inquiry Labs, which is a small Hungarian company for who works in model-driven system engineering, well, software engineering and applied R&D and IoT and stuff like that. And I will do the demo. For starters, I guess, since we are at the very end of the conference, I guess everybody now knows what Capella is, right? And EMF. Okay, so who haven't heard about EMF change before this presentation? Okay, so almost everyone. That's great. So what I'm going to show is that, okay, we have a couple of models. We have a master model that we are working on, internal, let's say. This is the in-flight entertainment system model that is a sample for Capella. You can download it and look at it, and it's quite a complex Capella model. And what the scenario that we are describing now is that we have a master model that our systems engineers are working on, and then we may have some suppliers who do some small parts of the system, and we have to collaborate with them. And when the model changes on our side, we have to see if there is some changes that they should know about, and then put the changes in their model and give it to them. So if you have, I guess you have seen a Capella model in some of the demonstrations. And here I can just show you that, well, we have in the system analysis level, we have a few system functions, and let's say that we have this maintenance part where there are some functions that have to be developed, and we I can see that, okay, we are working on it with my colleagues, and when I pulled my Git repository and looked at the state of the model, I could see that that there were some new changes. The model has changed in some way, and so I look and see, okay, what happened, and then okay, so this is the difference. My EMF model has changed, and I don't really know what happened, and I guess even for experts it would be very hard to see just from this what happened. Luckily, EMF Diff merge has now support for working with the team provider of Eclipse. So you can just say, okay, let me see what happened since the previous version. So you just compare the model with the previous version, and Diff merge will tell you, okay, this is what changed. And you can see here that basically you can see the two versions of the model. One in the commit is the previous version, this is the current version, and you can see here in the synthesis view the list of changes. So is there anyone who haven't seen Diff merge UI before? Oh, that's nice. Okay, so this is the Diff merge UI.
I don't claim the UI is fantastic.
Okay, so what you can do is select the differences and see where they are in the model, and you can also merge them. So, but obviously this is already merged. But if in the regular case, when you compare the models, you can then merge the differences. And what I want is, okay, I can see that there is a new function that is related to maintenance and testing. So this is something that the supplier should have. So what I do was select some parts of the model. And I can see also that the new function is allocated to one of the existing actors. So what I want to do is generate a patch from this. And I would just say, okay, I save it to the supplier's model, and this is the add test harness patch. And it's created, and I get a new editor which shows the patch that was created. I'm not sure how much you can see from the text. I'm not sure. I can try. Should I try enlarging it, or doesn't matter? So what you can see here is a list of model modifications in the patch. These are a sequence of changes, and well, yeah, this is the new function that was added, and okay, whatever. So what happened is that we compared the two models with Diff merge, and then we have a patch recorder which creates this patch that you can see now. And what's really important is that this patch is portable, so it's not directly referencing the model, and can be reused on another model as well. So what I wanted to do now is to apply this on the model of the supplier. And so I close this one and close this one. So I have here the supplier's model, which is not the complete model that we are working on. It's just some parts of it that are relevant for their work, let's say. here you can see that he has the maintenance and testing related functions for himself. And I can say, okay, I want to apply the changes, the model patch on this, this model. And I can select the patch. And then I can see, okay, yeah, this is the changes that will happen. And I get a feedback that, okay, we have applied the patches, we have resolved all of the changes, and we can see that, okay, they can be applied on this model. There are no problems. And so, okay, finished. Let's do this. And so you can see my model has changed. The new function has appeared. And, oh, that's great. So let's save it. And, okay, but what happened? So let's see. How did the model change precisely? So I can compare it with the head revision, the supplier's version in the source control, let's say, or the version control system, with the changes that I have just made. So we can see that yes, what happened is that we have the new function. You have a functional exchange between the new function and an existing function, and the new function is allocated to the actor. So this looks fine. And so okay, we can give this to the supplier, and he should be happy, and he can work on it more with the model. Yeah. So yes. So what happens here is that once again we use diff merge during the patch application. Is that we actually copy the original model and then apply the patches, the contents of the patch, and then we get the new model. And yeah, sorry. So and obviously it would be important for the user to see what happened during the patches before saving his model, so that he can decide what parts of the patch to apply and what happened during the patch application. So we can do that as well. For example, let's say that we have seen that in the version of the master model, there was another change, which was someone decided that the ground operator actor should be renamed ground operation manager, because that sounds more professional or something like that. But as a, I don't know, the responsible party or who should decide about this, I decided, okay, this shouldn't be done. So we should revert that. And obviously I could go to the model and do a change directly, but we can do that also with model patches. We can save the difference, that part of the difference, into a model patch, which I have done. And here we can see that, okay, this patch contains a change in the name attribute of a given element, with the old value being the ground operator and the new is the ground operation manager. And so I want to apply it in our master model. So I can go here and say, okay, apply model patch, and select this patch. Say next. Okay, this is what I want to do. Yeah. Next. And then it says, oh, okay, you can do that. Why? And we can see what happens. Yeah, it can be sent. So what it says that, okay, you cannot do that because the name of this element is not this one. So you cannot remove the ground operator value from the name attribute because it doesn't have the name doesn't have that value. So what you have to do instead is that, oh right, I remember I created the patch in the wrong direction. So I have to reverse it and apply it that way. So we can do that and just say, okay, this is the patch, and I just reverse it. So now we unset the ground operation manager and set it to the ground operator, and that works. So now, instead of clicking finish, which will just apply the changes in the model directly, you can say, okay, what happened actually? And here we can say you can see that the diff merge comparison viewer is embedded in the wizard for the model patch application, and we can see that there are two changes, which is just what we wanted, the changing of the name. So what I want to do is now merge these changes into the model, and I can select which changes to apply. And so even if I have a big model patch that someone gave it to me that, okay, these are the changes that I have made, do whatever you want with them. You can select which part to apply and selectively just merge them into your model and say, okay, this happens, that's good. And then, okay, no more changes to apply. And then now I can click finish, and now the changes have happened in the real model, not just the copied one. Yeah. So an interesting question is that, okay, but that's really nice. We have two wizards, and then they create a patch, and then you apply the patch, and you can use the diff merge UI to compare them. But how do they look like? How does this look like? So what we have is the patch is actually represented in memory in this very simple form. We have a model patch with an ordered list of entries, and the entry has a change type, whether we add it or remove it, and has a context, which is a so-called identifiable, which has an identifier. This is very important. This is how we decided that instead of referring to the model elements by let's say XMI, href, href, or the unique name or something like that, we want to say that, okay, elements in the patch are just identified elements, and someone should worry about when they apply the patch, the application code will use an identifier provider stuff to match the elements in the given model with the identifier in the entry. So then we have element entries for creating elements or deleting elements, and we have feature entries for setting feature references or attribute values. And obviously reference entries have target identifiable again. And then, okay, this is the in-memory representation, and the model patch framework, the model patch component has a runtime part where you can work with this internal representation. You can create it and save it and apply it on a model. And this looks like, and then when you save it, you have, by default, it saves it in a JSON format, which looks like this. Obviously, we have an editor where we could open the patch and see it in a list, and but otherwise it's in a JSON format, which is quite simple. We use Google JSON, which is a nice JSON-based library, and you can see that we have a list of entries, and the entry has a value and the feature and the direction and the context, and this is an attribute entry. And you can see that even the features in the EMF features are identified by an identifier instead of somehow directly referring to them. And okay, that's nice, but obviously the JSON is very nice for sending in an email or versioning in some way, since it's text. It's a simple text, and for compressing it. But what you want to, when you want to work on it, it may not be that great when you want to write code that works on the model patch representation. Obviously, you can use the internal objects, but sometimes that's not great because obviously EMF is very nice, and you have a lot of EMF-based tools. So what we have is that you can have a mapping between JSON and EMF-based representations of the model patch. And the other thing that you can see here is that the model patch application is changes the model. So obviously you have to be aware of editing domains, because, for example, Papyrus model will have a transaction editing domain, so it doesn't let you just call the setters on the model. So we have an option to use a so-called editing domain over model access, which will wrap all the application of the patch in commands, and so it works even on a Papyrus editor. So the EMF based on is selected now, so we can save this from the model patch editor. So this will be the EMF e-model patch, which can be again opened with the model patch editor, or it can be opened as a simple EMF model. So what you can see here is that this is a model patch which has entries, it has a metadata, and it has identifiables which contain the IDs that are used in this model patch. And obviously, since this is an EMF model, you can do whatever you want with it that you can do with an EMF model. And all the different parts of the patch UI and runtime are well, the patch UI, when you apply the model patch, it can realize that is it a JSON or an EMF-based model patch, and then apply it without problems, both of them. And so let me just check. Yeah. Okay. We also have a feature that is not really too complicated or refined at this point, but there is some starters, which is obviously in the editor you can also reverse the patch if you want. But the interesting thing is that you can add filters. So you can say that, okay, I want only the add or remove direction changes, or you can say that I want to filter out reference changes and just see, okay, these are the objects that will be created with these types, and these are the attribute changes that will happen. So you can filter the patch, and then you can save the filtered patch, and it will only contain the entries that you see here in this order. Yeah. So I think the last thing, because we are about time, is yes. So we have EMF-based model patches, and sorry. Yes. Okay. So what happens if I want to compare them, or let's say merge them? So I can do that. The only thing that I have to do is that to make diff merge happy is that I have to make sure that the IDs are of the root elements are at least the same, because then it can merge the contents without problems. So I just do this simple modification in one of the patches, and then now I can just say, okay, these two patches should be compared with diff merge as models, and this is very meta. Please don't kill me. Okay, so what we can see here is that one of the patches contains some entries and the other patch contains other entries. And if we, for some reason, want to merge two patches, we can just simply select some parts. I unselected the metadata because both parts contain the metadata, and if I merge this, I can merge this, but then it will override the other model's metadata, which may or may not be okay, but doesn't matter. And then we can say, okay, I want to merge this. So it will add those parts to the other model, which you can save. And then obviously you will have a model patch, I think that one, which will contain all the entries from both your patches, because you just merged the two models. Okay, so that was about it. If we could evaluate the attendees, then all of you would get a +1, because this is the last presentation of the Eclipse Con, and we have very, very strong competition in the other rooms. So thanks for being here. Be sure to evaluate the session, and if you have any questions or need help staying alive, we have the examples on the GitHub repo. You can try those out, the models I have shown you. And here are some links for the companies. So thanks for being here.
Thanks.
Yeah.
Yeah. According to your slide, we have two kinds of change types, right? Addition and removal.
Yes.
And I'm wondering if you thought also to have some more, a third type, so it change. For instance, when you want to change the value of an attribute.
Yeah.
Because of course you can obtain the same result by simply removing and adding an attribute with different name, but this semantically will be different. And we reduce the possibility of using this information, for instance, for adapting other artifacts that depends on the patch that you are storing.
Okay.
Yeah.
Okay, so thanks for the question. Yes, we had put in a lot of thought when we created the internal representation of the patch. And yeah, it was quite one of the questions is, okay, what kind of change types is there? Should there be a move or an update or something else? And we decided that we want to make the model patches, let's say, to contain atomic changes and to be able to make sure that every kind of model change can be only described in one way. So you don't have redundancy in the model in a way that you can describe the same change in two different ways.
It's the same philosophy as in the EMF Diff merge itself. We wanted to separate concerns. There's first the ability to have things done, things working, and so the idea was provide the minimal lowest possible level concepts. And on top of that, we can build user level, more semantic oriented representations. But I think it's good to distinguish the two.
Can I have also a question?
There's another. For the context, for example, and the target, well, we said that the same way as EMF Diff merge says that you have to have IDs for the E-objects, we said that there should be an ID. So it can be only used if you can map an object, an E-object, or a model element to a unique ID.
I can elaborate a bit on that. In fact, what you have for the diff merge to work, you need to be able to associate to any model element that you are comparing an object, a Java object of any kind, which identifies the element. And two elements will match if and only if the corresponding object, the match keys are identical, equals in Java. But it doesn't have to be a proper ID. It could be a qualified name. It could be any object that represents the semantics of the element in any semantical representation, for example. So in the demo, Abel tweaked a bit the ID, but now in a new version of diff merge, you have by default a certain number of match policies that allow you to use structural constraints in your models to infer matches instead of just systematically using IDs. This is something we've been doing for quite some time in Thales, but now we have put some of these policies in open source.
Yeah, and I think I didn't answer your specific question. So how we do it in general with the tool? We just basically, EMF has this sort of get ID feature. So if your meta model if your E-class has a features marked as an identifier, then we use that in the patch. If it doesn't have, then it doesn't work, but the framework itself is built in a way that this sort of, what is the ID of an object and what is the object for a given ID is put in from the outside. So you can have your own, any kind of meta model, any kind of strategy for mapping the IDs and the objects, and the patch will just contain the ID that you give the patch recorder for a given object.
When you have conflicts, how do you solve them when the patch conflicts with your own changes? We saw, for example, where we had a pop-up because the patch was done in the wrong way, so I guess it's the same pop-up which shows when you have conflicts. And how can you solve them in the UI?
Yeah, so the simple answer would be that in this case, you could see that the next button on that page was still enabled. So because the patch application goes through all the whole patch and will try each change, and even some of those will report diagnostic errors, and those are put on the table, but other changes are still applied. So you can go to the next page and see what were the changes that have been successfully applied, and you can compare with your model, and then you can even merge those and have some changes. But as far as how do you deal with the errors that are shown, well, basically it shows that this entry was problematic, so hopefully the description is good enough that you can see, okay, why it happens, but there's no explicit conflict resolution on that way.
The idea is that we have the base technology that works, but obviously if we wanted to have it very user-friendly, we would need more work on the UI and stuff for sure, which is always the costly part, right?
Yeah.
Sure.
So I'm curious about the generation of the patch. In particular, you mentioned that you are comparing two versions of the same model,
Yes.
and the difference consists of the addition of a new object, and this object refers to an element existing to the previous, the initial version of the model.
Yes.
So the patch will consist of this addition of this object. Now, you said that the patch can be applied to any models, even different than the one that you used for calculating the patch.
Yes.
Now, imagine that you are applying this patch to another model, and this model does not contain the type of the reference that you had in the patch. So what happens in this case?
Well, obviously you will get an error on the application that this entry couldn't be applied. It can be, I think we have a different error message for when the feature is not existent that you want to change. If you have a model with a different meta model, I don't know if that was what you were asking. So if you want to apply the patch on a different model, which is with a different meta model, then obviously if it cannot be mapped directly, which it probably won't, then you will get errors that there is no feature to set. If it's just a completely different model, but in the same meta model, like for the Capella model, that's why we have identifiers, is that if the identifiers exist in the model, then it will map those to that, and then just say, okay, if you have two unique IDs, which should be almost completely unique, or yes, at least inside the model, then they are probably the same element. So compared to what? Yes. Yeah. Yeah, ordered. It means that the entries in the model patch must be applied in the sequence that they are stored. So obviously you. Yeah, the sequence is that's the part of the patch recording. So obviously when we have the difference between two models, that's an unordered difference, because it just say, okay, there is an element here that is not here, and there is an attribute change here that is not a different value here. And the patch recording basically goes through the diff merge, diff data model, the internal representation of the difference in diff merge, and well, basically you order the different type of differences, whether it's an addition or deletion, an element, a reference, or an attribute change, and there is and obviously you have to look at the containment. Actually, you don't have to look at the containment. So basically, it orders these as the different types, and it ensures that the order that it stores them will be applicable. And there is one trick with and that's why I said that the containment doesn't have to be evaluated for the ordering, because we basically says that, and that's why the element entry is separated, is that we can create an element, store it in a temporal place, and know that, okay, this is an ID, an element with a given ID, and then if later someone says that this reference should be set to this element, then we just set it. And if for some reason this is a containment reference, then it will be put under that element. And if you think about it, it doesn't matter in what order you create the elements, and in what order you set the containment references, at the end, the containment will be correct. And if just this very simple, you have to first create the elements, or first delete the attributes, then delete the references, then delete the elements, and the other way around. That's why the reversing is very simple, because we simply change the change type to the other one and reverse the list. That's it. Sorry?
Is it possible to have a model who returns another model and create a patch which change on the other?
Yeah, but basically we abstract away from the resources or models. So basically you have an EMF model in memory in as many resources as you have, or any time, any type. We just basically have to be able to select any element that with a given ID. As long as that works, it doesn't matter where those model elements come from. It can be multiple resources.
Yeah, the difference itself operates at a strictly logical layer. It doesn't care about resources at all,
Yeah.
and it's the same kind of working for patches.
Yeah, I think we have to move because the closing session starts. So if you have any questions later, we are still here.
We're here.
Thanks.
Well, not in this
Not
room,
here.
but, thanks to you.